I wanted to do a couple more examples that allow us to use the kinematic equations, but we can't use the kinematic equations, meaning the big three, in just one step, meaning for the problem as a whole. So reading through here, we're driving down a highway late one night at 20 meters per second. There's a deer in front of us. We have our reaction time before stepping on the brakes, and then when we step on the brakes, we slow down to stop. So ultimately, we want to find out how much distance is between us, you, the deer, and the deer when we finally come to a stop. So the acceleration, if you remember, the kinematic equations can only be used if we know for sure that the acceleration is constant. And it has to be constant for the entire time period we are using them for, these equations. So we do need to be careful. During the time before we actually react, that half a second, us in the car, we continue traveling at 20 meters per second. There is not an acceleration during that time. But of course, once we step on the brakes and slow down, we have an acceleration. Let me get the third equation written out here. We can totally break this into parts. One part where we're talking about our reaction time, when the acceleration is 0, and one part while we are braking. So I'm going to make a rough sketch, as usual, and I'll say where we are in the car originally, traveling at 20 meters per second, is my origin, or is our origin. So similar to the previous problems, we still want to make a list of the variables that show up in the kinematic equations and fill in what we know. By putting our origin where the car is originally, that makes the initial position 0 in this frame. And then, let's see, S final, we don't know, but we will need to figure out how far we travel in that half a second. We do know the initial is 20 meters per second. We do know our acceleration is 0, which does mean our final velocity is 20 meters per second as well. Because, again, the definition of acceleration is a change in velocity in some period of time. So if there's no acceleration, our velocity is not changing. They do give us the time for this portion. So ultimately what we can figure out is how far we travel in that half a second. Acceleration is constant. It's constantly 0 for that half a second. So we can use the kinematic equations. I'm going to go ahead and choose the middle one, because we want to find out how far we've traveled. Now I'm writing the whole thing out because we want to show what equation we're using, and then we can go ahead and zero out. So this ends up being a fairly simple calculation. We know we're traveling 20 meters per second for half a second, so we will have traveled 10 meters in that half a second. That's a pretty decent distance. So now we want to come over, and we're talking now about having our foot on the brake. We're assuming the brakes are locking and we're decelerating or slowing down at that rate of 10 meters per second squared for the rest of our traveling until we stop. So ultimately, we've traveled 10 meters. We're still traveling 20 meters per second, but now we're stepping on the brake and we're going to slow down and stop. The approach is still the same. We can use the kinematic equations simply because we know this acceleration is constant. we're going to assume this maximum 10 meters per second squared. And we do need to make it negative to account for it slowing us down. In my sketch, I went ahead and made our velocity to the right, meaning positive. And so to slow down, the acceleration needs to be opposite, so to the left. Excuse me. So our initial position, we do have choices here. We can set up a new origin, and then our final position will be measured from that new origin, or we can just keep our initial origin of back where before we even reacted. We can say we are now 10 meters away from that location, and we can find this final position to then figure out how far away we are from the deer. Our initial velocity at the moment we step on the brakes is 20 meters per second. We know we are stopping, so V final is 0. Again, we want S final. There's two ways to go about this. If we want to use the middle equation again, we need to find time first. But finding time from the top equation would be easy enough to do, so we can totally do that. The other option is to use this third equation. Delta S, remember, means S final minus S initial. So we can solve for S final that way as well. One way is not necessarily any better than the other. This is a matter of opinion. So I guess since I'm at this screen, I'll choose. Let's go ahead and just use the third one. So I'm going to go ahead and write that equation down. If we were taking a test or doing the homework, we wouldn't write all three equations out every single time. At least I wouldn't. So I know V final is 0. We have V initial. So I'm going to bring V initial over to I'm going to put in our S final minus S initial for delta S. I'm looking for S final. So I'll go ahead and divide by 2A and then add S initial to the other side. So minus V initial is 20 squared. The minus sign is outside of the V squared, so I do not square that negative and make it positive. So 2, our acceleration is negative 10, and our initial position was 10, because that's how far we traveled while reacting. So we get we get 30 meters here. Now this is not our final answer. The question is asking us how much distance is between you and the deer. So if we come up to our picture, we've traveled a total of 30 meters from when we first saw the deer. It tells us that the deer is 35 meters away, so the deer is over here 35 meters away. So our answer is we are 5 meters away from the deer when we stop. And that's what the question asked for. Again, we had to break into parts. The reaction time part separate from the braking part, simply because they have different accelerations. No acceleration during the reaction time, and an acceleration slowing us down at 10 meters per second squared.